Welcome to the deep dive. Today we're embarking on a journey into the quantum realm.
That's right.
Specifically, we want to unpack the fascinating discovery of tunneling supercurrents.
And our main source here is the Nobel lecture given by the person who figured it out, Brian D. Josephson.
Exactly. So our mission really is to get beyond just the dates and facts.
Yeah, we want to understand the core ideas, those aha moments, and honestly, the pretty surprising ways this whole thing changed things. Josephson's lecture gives us this amazing inside look at his thinking process.
Okay, so let's dive in. Where did Josephson's curiosity really kick off? It seems to start with this idea of broken symmetry in superconductors.
Right, broken symmetry.
Sounds quite abstract. What is that and why was it so important?
Well, the idea itself wasn't totally new, but Phil Anderson really brought it to the forefront for superconductivity around 1958. He developed this really clever way to visualize it using something called pseudospins.
Pseudospins. Okay, not actual spins.
No, not literal electron spin. It's more like an analogy. Imagine you have pairs of electron states, opposite momentum, opposite spin. If both states in a pair are empty, think of a little arrow pointing up, both full, arrow points down.
Okay. Like a shorthand.
Exactly. And if it's a mix, one occupied, one not, which is what happens in superconductivity, the arrow points somewhere in between. It's just a representation.
Got it. A visual tool.
Yeah.
And how does this connect to the energy of the superconductor?
So Anderson wrote down an equation, the Hamiltonian, right? It described the energy. It had parts for the individual pseudospins moving and parts for how they interact. Now, on a regular metal, these pseudospin arrows are pretty simple. They're all lined up, either pointing straight up or straight down, and they flip right at the Fermi surface, that energy level dividing filled and empty states.
Okay, neat alignment.
But in a superconductor, things are different because the electrons attract each other. This attraction makes the pseudospin arrows tilt. They all tilt together in a plane. And here's the key bit. The angle of that tilt changes smoothly as you go across the Fermi surface. It's not an abrupt flip like in the normal metal.
So that coordinated continuous tilting.
Yeah.
That's the broken symmetry.
Precisely. The superconductor, in this ground state with all the tilted spins, it sort of lacks a symmetry that the original equations had. The original math allowed rotation around that up-down axis, but the tilted state picks a specific direction in the plane. This means there isn't just one single ground state, but actually a whole family of them, all equally possible, just differing by this angle, this phase.
Okay.
And Anderson made the connection. This angle was basically the same as the phase of this complex quantity F that Gorkov had used in his very powerful theory of superconductivity.
Right. So Josephson sees this connection,
Yeah.
this hidden phase angle emerging from the theory. What was the next step in his thinking?
Well, he started wondering, okay, this phase exists theoretically, but can we see it? Can we measure it somehow?
But wait, if the original system has this rotational symmetry, wouldn't the absolute value of EV-K be like fundamentally unobservable?
Exactly. The absolute phase of a single isolated superconductor, yeah, you probably can't measure that directly. It's like trying to measure absolute potential. But Josephson thought, what about the difference in phase between two separate superconductors?
Okay, a relative phase.
Right. Could that difference have observable consequences? For that to happen, though, the two superconductors would need to be linked somehow. They'd need to be able to exchange electrons.
Like a quantum connection.
Sort of, yeah. Think of it like they need to know about each other's phase. This connects to the uncertainty principle between particle number and phase. If you fix the number of electrons perfectly, you lose phase information, and vice versa. To see the phase difference, you need some electron transfer.
And this is where those earlier experiments come in. People had seen supercurrents flowing across thin, normal regions, right? Not insulators, but normal metal gaps.
Exactly. There were reports of this happening. So current was getting across this non-superconducting barrier. That hinted that maybe, just maybe, this path could allow the phase difference to manifest itself.
So he suspected the supercurrent across the gap might depend on this phase difference peak.
That was the intuition. He thought, okay, the size of the supercurrent should be a function of A. Makes sense theoretically. But actually sitting down and calculating that function, he initially thought it looked, well, incredibly difficult. The math seemed really tough.
Okay, so the stage is set. We have broken symmetry, a potentially observable phase difference, hints from experiments, but a difficult calculation. What was the breakthrough? What pushed him forward?
A really key moment was learning about Ivar Jeever's experiments. Jeever was looking at electrons tunneling between superconductors, but separated by a very thin insulating barrier, like an oxide layer.
An insulator. Not a normal metal this time. That seems like a harder barrier to cross.
It does. And interestingly, Pippard, a really big name in the field, had actually thought about Cooper pairs, the electron pairs in superconductors, tunneling through an insulator. But he basically argued it wouldn't happen. He thought the probability was just vanishingly small, essentially zero for any practical barrier.
So the common thinking was pairs can't make that jump. How did Josephson approach it differently?
Well, instead of focusing only on whether the pairs themselves could tunnel, Josephson started thinking differently. He wondered if the phase difference could somehow affect the tunneling of normal electrons or quasi-particles across the barrier.
Influencing the regular current, not necessarily being a pair current itself.
Kind of. He was thinking about these things called coherence factors. They pop up in the theory of superconductivity and are related to this broken symmetry to the phase A. He thought maybe these factors modify how likely single electrons are to tunnel. The trouble was, back then, there wasn't really a solid fundamental theory for tunneling current through these barriers. Javer had found some useful formulas based on his experiments, but it was more heuristic.
Right, empirical findings rather than a deep theory. But Josephson managed to predict something quite specific about time, didn't he?
Yes, this was crucial. He drew on another insight from Gorkov's work. Gorkov had pointed out that this F function, the one related to the phase A, was essentially proportional to e to the power of I times mo times to e over h bar, where me is the chemical potential, the energy level.
Okay, a link between phase and energy over time.
Exactly. From that, Josephson derived a relationship for how the phase itself should evolve in time. It basically says the rate of change of phase is related to the chemical potential, or energy. And then the really important step. If you have two superconductors with a voltage difference V between them, their chemical potentials are different.
Right, the voltage creates an energy difference.
Precisely. And so the difference in their phases, day, changes over time at a rate proportional to that voltage V. Specifically, the rate is 2AV bar.
2 eV. So related to the charge of a Cooper pair, 2e times the voltage. What did that imply?
It implied something remarkable. Think about it. The phase difference is changing linearly with time if the voltage is constant. But the physics of the system shouldn't fundamentally change if the phase difference increases by a full cycle, by 2 car, right?
Right, adding 2 to an angle doesn't change its physical meaning.
So if the phase difference affects the current and the phase difference is cycling like this, then the current itself must be oscillating back and forth.
An alternating current.
An alternating current, yes, at a frequency given by 2 of VH. This was the prediction of the AC Josephson effect, a current oscillating purely because of a DC voltage difference across the insulator.
Wow, that's really counterintuitive. An AC current from a DC voltage source with no oscillating input.
Highly counterintuitive. It suggests energy from the DC source is being converted into AC energy in the junction, a truly wild prediction at the time.
Okay, so he has this prediction for an AC current. But what about the DC supercurrent? The one he initially thought might depend on, though. How did he finally calculate that?
The calculation part came together thanks to, well, a bit of timely help. Phil Anderson shared a preprint of a paper by Cohen, Felikov, and Phillips. They had tackled a related problem, calculating the current between a superconductor, a barrier, and a normal metal. And they had confirmed Javer's experimental formula, which was a big step.
What was their approach?
They used a really clever method. Instead of trying to directly model the tunneling process, they used the fundamental principle of charge conservation. They said, look, the current flowing into the barrier must equal the rate at which charge builds up or depletes on one side. They calculated this rate of change of charge using quantum mechanical perturbation theory. It was a new way of looking at it.
And Josephson realized he could use their technique for his setup superconductor, barrier superconductor.
Exactly. He adapted their mathematical machinery to the superconductor insulator superconductor case. And when he worked through the calculation, he got an expression for the total current that depended on the voltage V and that phase difference bay. It had basically 3 main parts.
3 parts. What were they?
Okay, so the first term, let's call it J1, looked pretty much like Javer's normal tunneling current. It depended on voltage in the usual way. The second term, J2, was a bit different. It represented quasi-particle tunneling, but it also had this interesting dependence on the cosine of the phase difference, cos.
Okay, so the phase difference was affecting the quasi-particle current too. And the third term?
The third term, Js, was the real surprise. It was proportional to sin, the sign of the phase difference. What was really striking about this term was, first, it was an even function of voltage, meaning it didn't care about the direction of z. And second, crucially, it was non-zero even when the voltage V was exactly zero.
A current with no voltage.
That was it. Josephson identified this Js term as the tunneling supercurrent he had been looking for.
The DC Josephson effect.
Precisely. His theory predicted that a supercurrent up to a maximum value Jc, the critical current, determined when sin is 1, could flow across the insulating barrier with absolutely zero voltage drop.
And what about at finite voltages? Did the calculation also confirm the AC effect?
Yes, the calculation inherently included that too. At finite V, the sin term oscillates because A is changing with time, as we discussed. So it predicted an AC supercurrent oscillating at frequency 2 AVH with an amplitude related to that critical current Jc.
So the theory gave this complete picture. A zero voltage DC supercurrent up to a limit, and then AC supercurrent when a voltage is applied. What did that predict for the overall current voltage graph?
It predicted a really distinctive shape. You'd see zero voltage across the junction for any current up to the critical current Jc. Then, bang! As soon as you try to push more current than Jc, a voltage suddenly appears, and the current flow switches over to the normal electron quasi-particle tunneling regime, following more like Geiger's curve.
A sharp jump. Okay, the theory sounds solid, predicting these pretty wild effects. But getting it confirmed experimentally? That sounds like it might have been tricky.
It absolutely was. There was an initial slight embarrassment, actually.
Oh, was that?
When Josephson first estimated the size of this predicted supercurrent, the theory suggested it should be proportional to the normal state conductivity of the junction, how easily normal electrons tunnel. This implied that for typical experimental setups, the supercurrent should have been relatively large, maybe easily measurable.
But it wasn't always seen.
Not consistently, no. He went back and looked through the literature. There were some older reports, like from Nicole, Shapiro, and Smith, that showed characteristics sort of like what he predicted a zero voltage current.
Okay, so maybe it had been seen.
Well, the problem was these observations were often just dismissed. People, including Geiger himself, tended to think they were just tiny metallic bridges, microscopic shorts through the insulating barrier, not some exotic quantum tunneling effect.
The mundane explanation seems simpler.
Exactly. If you have a tiny hole in your insulator, of course current can flow with no voltage. So Josephson's prediction of a tunneling supercurrent was initially met with some skepticism because the short-circuit explanation seemed readily available. Must have been a bit frustrating for him.
I can imagine. So how did they eventually distinguish between a real Josephson supercurrent and just a tiny short?
That's where Phil Anderson came in again with some crucial insights. First, he suggested that maybe external magnetic fields were messing things up. Even the Earth's magnetic field, though weak, might be enough to suppress this delicate supercurrent in some experiments, explaining why it wasn't always seen.
Okay, so shielding might help.
Josephson actually tried that. He set up an experiment trying to compensate for the Earth's field, but didn't immediately succeed in seeing the effect clearly. It wasn't quite that simple.
So what else could be hiding it?
Anderson later realized something else. In many early experiments, the junctions had relatively high electrical resistance. And in high-resistance junctions, even tiny amounts of electrical noise stray signals bouncing around the circuit could generate currents large enough to exceed the predicted critical supercurrent, Jc.
So the noise was effectively switching the junction out of the superconducting state before they could even see it.
Exactly. It was just enough disturbance to push it over the edge and hide the zero-voltage state. The breakthrough really came when Anderson and John Rowell did experiments using junctions specifically designed to have much lower resistance.
Lower resistance, less susceptible to noise.
Right. And with these low-resistance junctions, they finally saw clear, unambiguous evidence of the tunneling supercurrent. But the clincher, the thing that really proved it wasn't just a short circuit, was how incredibly sensitive this current was to magnetic fields.
Back to the magnetic field idea.
Yes. They showed that applying even a very small magnetic field could dramatically reduce or even completely quench the supercurrent. You wouldn't expect a simple metallic short to be that sensitive. They even saw the critical current increase when they carefully nulled out the Earth's field.
That sensitivity. That sounds almost magical. Is that the basis for those super-sensitive magnetometers, the SCU-DZ?
Precisely. That extreme sensitivity is the whole point. But there was more. Rahl then did detailed studies mapping out exactly how the maximum supercurrent changed as you varied the magnetic field strength. And the pattern he saw looked remarkably like.
Well, like the diffraction patterns you see when light passes through a slit. J.C. Phillips apparently pointed out this analogy.
Wow, diffraction patterns with electron currents, that's deeply quantum.
It absolutely is, and it got even better. Another group, Yakovlevich, Lamb, Silver, and Mercereau, did an amazing experiment. They put two Josephson junctions side by side in parallel, and they observed interference effects between the supercurrents flowing through the two junctions. It was just like the famous Young's double-slit experiment, but with superconducting currents instead of light waves.
Quantum interference on a macroscopic scale.
Exactly. That really cemented the wave-like quantum nature of the whole phenomenon. And yes, this extreme sensitivity and the interference effects are precisely what led Zimmermann and Silver to develop SQUIFOIDs, superconducting quantum interference devices, which are the most sensitive detectors of magnetic fields we have. Incredible. Okay, so the DC effect and its weird magnetic field dependence were nailed down. What about the AC effect, the oscillating current? How was that confirmed?
That took a bit longer, and the first evidence was actually indirect. A researcher named Shapiro was doing experiments where he shone microwaves onto a Josephson junction.
Microwave, so applying an AC signal.
Right, and he observed something strange in the junction's DC current voltage curve. Steps appeared. Little flat steps at specific voltage values.
It's dub steps.
Well, Josephson's theory predicted that the junction's internal AC supercurrent, at frequency 2AV, could interact or mix with the external microwave frequency. This mixing leads to a DC component, a zero-frequency beat, only when the voltage V is such that 2AV is an exact multiple of the microwave frequency.
Ah, so the steps occur at voltages locked to the microwave frequency.
Precisely. The voltage spacing of the steps was directly proportional to the microwave frequency, with the proportionality constant being H2E. This was powerful confirmation of the AC effect's underlying physics.
And this had practical uses too, right?
Immense practical uses. Langenberg, Parker, and Taylor realized they could turn this around. By measuring the microwave frequency and the step voltage very precisely, they could get an incredibly accurate value for the fundamental constant ratio H2E. Their measurements were so good, they actually led to adjustments in the accepted values of fundamental constants.
Wow. From a weird quantum effect to refining fundamental constant.
Absolutely. And today, this AC Josephson effect is actually used as the primary voltage standard in metrology labs around the world. They define the volt using it.
So was the radiation from the AC effect ever directly detected?
Yes, eventually it was. It's very weak, so it was challenging. Javer himself managed it later, and also a group in the Soviet Union. Janssen, Svestunov, and Dimitrenko, they detected the faint microwave radiation emitted by the junction when it was biased at a DC voltage.
Okay, direct confirmation too. And the lecture wraps up with this story about the SLUG. Sounds intriguing.
Ah, yes, the SLU. It's a great example of serendipity in science. It stands for Superconducting Low-Temperature Ultraminiature Galvanometer. John Clark developed it. It came about because niobium, which is a useful superconductor, is actually quite difficult to solder properly. You often end up with a thin, unwanted oxide layer at the joint.
The insulating barrier again.
Exactly. These accidental, poorly controlled oxide layers were forming Josephson junctions right there in the solder joint. Now, these blob junctions weren't very good for detecting external magnetic fields like a proper SQUID, but Clark noticed they were extremely sensitive to the magnetic field produced by a current flowing in a wire right next to the blob.
So not measuring ambient fields, but measuring current nearby.
Right. It turned out to be a fantastic way to make an incredibly sensitive detector for very small currents. A different application born from a practical annoyance.
That's brilliant. Okay, so let's try and wrap this up. We've gone from this quite abstract idea of broken symmetry,
Which sparked the question of observable phase differences.
leading to these, frankly, bizarre theoretical predictions of DC and AC supercurrents tumbling through insulators.
Predictions that faced initial skepticism, experimental hurdles like noise and shorts.
But were eventually confirmed through careful experiments showing that unique magnetic field sensitivity, the diffraction, the interference.
And ultimately blossomed into a cornerstone of physics, giving us squeeides, voltage standards, precise measurements of constants. It's really quite a story.
It truly is. What strikes me is how these, really deep, almost philosophical quantum ideas, symmetry breaking, phase coherence, actually manifest on a scale we can see and use. A simple little junction becomes this macroscopic quantum object.
That's the wonder of it. It's not just theory, it's tangible. That tiny barrier between two superconductors is a direct window into quantum mechanics, and it turns out to be incredibly useful.
The impact is just huge, isn't it? From fundamental science measuring H2E to technology that lets us probe tiny magnetic fields from the brain or in material science.
Absolutely. It really makes you stop and think, doesn't it?
It does. And it leaves you wondering, what other, maybe equally counterintuitive quantum effects might still be hidden, just waiting for someone to connect the theoretical dots and figure out how to observe them? What other transformative technologies might be lurking in the quantum realm?
That's the perfect question to ponder. Thanks for joining us on this deep dive.